My name is Anshu Bahadur. My background is my roots are in semiconductor manufacturing, and therefore you'll find a bias here. I'll be a strong semiconductor bias, which is natural given the circumstances. So just like to thank Rishi, Nilesh, and Aparna, my team, before we get started. Here's the agenda. We'll start off first with Dr. Prith Banerjee from ANSYS. I don't think so Dr. Banerjee needs any introduction. Most of us in the semiconductor world know him. He's the CTO for ANSYS, has an illustrious career. He was previously at Schneider Electric, ABB, and at Accenture. Previously, he was in the academia, a professor and chairman and dean at University of Illinois and Northwestern Industries. He's also an entrepreneur and on various boards. I'd like to welcome Dr. Banerjee.
Everybody's talking about smart factories. This has been a topic for some time, but it is really relevant because of what is happening in the US, right? Everybody's talking about let's bring smart manufacturing to the US. You have all heard of the CHIPS Act, so I just wanted to show one specific thing, right? As part of the CHIPS Act, President Biden is giving $6 billion to TSMC. And in exchange, TSMC is putting $65 billion in 3 fabs in Phoenix, Arizona, right? And so there's stuff that you can do with making factories smart, right? You have a brownfield factory and you try to do some sort of changes to the factory and so on and so forth, versus the opportunity when you're building brand new factories. And it's not just TSMC. There's Intel building factories, there's TI building factories, Micron building, everybody's building a new factory here to bring manufacturing back, right? So the opportunity of AI-driven digital twins and smart factories is phenomenal. Now I should tell you that we don't have a product from ANSYS. I'm not going to sell anything. I'm giving this futuristic talk because this is TiEcon. I'm hoping to motivate 1 or 2 of you to take some of these ideas and run with it, right? But this is not going to be a single startup company play. It's an ecosystem play, right? When you have a thing like a TSMC, right, a factory, right, there will be equipment from Applied Materials. And I'm honored to have Om Nalamasu in the audience, right? He's going to watch what I say here. He's just super, super smart person. We are actually working with Applied. We are working, so you have to work with Rockwell Automation. We have to work with PTC. We have to work with AWS. I see AWS people here, Azure. So it is an ecosystem play, but I want to show what the opportunity is for this, right? And there are a bunch of slides, but I'll focus in on a few technical issues. So first thing is, what is a smart factory of the future, right? So, I mean, there are these sort of widgets that you have, right? You have in a normal, so I'll start with a general factory where you're making cars. I mean, there are people from Volkswagen here and so on, right? So you're assembling cars, right? In the past, they used to be built by humans, right? Some guy went in there with a drill and were doing things. Now it's through automation, right? Again, as some of you know, I used to be CTO at ABB, CTO at Schneider Electric. These are the companies, so I know what is the art of the possible with automation, right? And so now you can put all those things in the factory, right? All the equipment in all those lines, you can put all these sort of robotics and automation. Then you can put IoT and sensors and bring what is called the physical and digital worlds together. What does that mean? You have a physical equipment and you put IoT sensors on it and you pull data from that, and that pulls data from the physical world to the digital world. And then you can do the reverse, right? You put things on it and you watch things on your 3D screen, right? With all those the wonderful 3D glasses and so on, right? And that's stuff that you see on the metaverse or omniverse and so on, right? And that's bringing things from the physical world to the digital world. So that's what is going on. And then there's sort of stuff that I want to talk about, the future of factories, right? I mean, essentially in the past, cars and airplanes and so on used to be built with CAD tools and whatever, right? It was a very waterfallish process. You do this and you do the other thing and so on, right? But now with AI and now with CAD on the cloud and CAE on the cloud. You can do things with collaboration that you couldn't do in the past. And with the new types of manufacturing with 3D printing, which is what I'm showing here, right? I mean, you can, with Gen AI, you can imagine things that you would not do for normal factories, right? In normal factories, say, I need to have a molding machine or whatever, right? You could only do certain things in technologies from 60 years ago. Today, with 3D printing, you can do crazy stuff, right? And so how do you do the crazy stuff with Gen AI, generative design, tied with manufacturing, right? And then, of course, there's stuff that I just don't have time to go into, the whole talk of sort of software-defined intelligent systems, software-defined vehicles, right? Where you make a vehicle, you make a Tesla car, but then you keep on updating the software in the car, right, to do all these intelligent systems. So this world is completely transforming around us, which is why AI, ubiquity, etc., is so relevant in our area. So I just wanted to show you a vision from NVIDIA, right? And again, I don't work for NVIDIA, but Jensen gave a GTC keynote last year, right? Where he brought the leaders of manufacturing from BMWs to the stage and says, this is the art of the possible, right? So BMW making a new smart factory in Germany, right? So where they'll assemble cars with automation. But to say, hey, what is the art of the possible? So before building the factory, they built a model of the factory on the metaverse, on Omniverse, right? Metaverse is the general term, Omniverse, right? And so you have all these things are pictures. They look like real things, but these are images, right? Video images of, here is a factory, it's an ABB robot doing things. So you do the entire layout of the factory, do what if scenarios, says, hey, I need to generate this or this, and so on, you can do that. So I show it because I'm going to end my talk with what we are doing with NVIDIA on smart factories. So then the question is, I'm going to start with a general factory, right? In a general factory, I'm not talking of semiconductors, I go to semiconductors next, right? You have to do basic things like, you have to do metal forming, right? You have a sheet metal, and before you put it in the form of a car door, right? You have to smash this thing, right, and make it into a form, right? So that's called metal forming. You have to do forging, you have to weld things together, you have to shear, you have to bend. These are all complex mechanical processes, right? These are done by machines, but you have to model what is going on in these mechanical processes. And so all the things that are being done by equipment in the factory, you need to have a manufacturing process and model. And this is where ANSYS comes in, right? The world around us is governed by the laws of physics, right? Physics does not lie, right? You have all gone to, some of you have gone to engineering classes, right? You've done these things called trusses, right? You have this big beam, and it's on this side, and I put some pressure on it, and how much will it bend? For a simple beam, you can do analytically. But for really complicated, convoluted beams, right, you need to do numerical method simulation to do it, and that's what ANSYS does, right? So all the processes, metal forming, this thing, gear forging, all the things that I talked about, there is actually a simulation model to do it, right? But we have not actually applied to factories, right? So this is literally a new thing I'm talking about for ANSYS. I'm going to pitch this to ANSYS also, that we need to get into this area, right? The trouble with this is, yes, there is a simulation model. The trouble is these models take like 10,000 hours to run just to do this one little metal forming, right? So on an NVIDIA metaverse model of a factory, right, you can say, yeah, I have this factory and BMW guys, but I'm about to do the welding, but just one step, it will take you 10,000 hours. So it's clearly not real time, right? So there are simulation methods that exist to model all these things, but they're not fast enough. How do you make it fast enough is through AI and GPUs and so on, which is why I will end with that, right? But this was about the general factories. Now I started with semiconductor factories, right? So it's semiconductor, there are these different processes, right? And so again, and there's people from Applied in the room, and so I don't want to even go there, but there's processes like semiconductor fabrication, there's assembly packaging, there's a sort of a chemical vapor deposition, all those different things. And again, you're doing those processes, but you need to have models. So this is a slide that is part of the collaboration between ANSYS and Applied, right? So I want you to understand. So you are doing, ultimately you're trying to create a FinFET, a transistor. But it has to go through these 100 different steps, right? Using equipment from, say, Applied, and I'm sure Ala during his panel will talk about it, right? So you start with just a reactor, right? One of those chambers from Applied or from Lam or one of those things, right? And you're saying I create an equipment model, right? And that equipment follows physics. That physics can be simulated by ANSYS. The trouble is it takes a long time to do one step of one process, right? So we'll come to that, how to accelerate it. But you start with the equipment model. Then as part of the equipment, you have these 10 steps you have to do to get to that FinFET. You have to model the whole process, and then you model the FinFET or the IGBT or whatever you make. And what you're trying to do with this digital twin model is, can we help TSMC or Samsung saying, you tweak this and you'll get 1% more yield. If you can, through AI and digital twinning, if you can improve the productivity, right, just by 1%, it's billions. That is the opportunity, that is the ROI. So now let me this is the one slide that I will talk about ANSYS, right? We are a leading simulation company. We have all kinds of physics-based simulation products, from structural software to fluid software to electromagnetic software to whatever. But these things on the bottom, they are super accurate, but they take a long time to run. So it will not work, right? So you have to build a digital twin model, which will go very, very quickly. So to do that, I have to have a job. So as CTO at ANSYS, my job is to, what is the future of simulation? So we are doing things around using high-performance computing like GPUs, the Blackwell GPUs from NVIDIA, for example, or AI/ML, or cloud, right? We have people from AWS and Azure here, right? I mean, HPC on the cloud on steroids is how simulation will get greatly accelerated, and others, right? Just to give you a flavor of how AI can work, right? Our world deals with numerical methods, physics-based simulation. Takes a long time to run. Turns out, we just announced this thing called SimAI, right? Which you upload one design, right? Here is a model of a Ford Explorer. You upload that, and you do a little bit of external aerodynamics of this car, right? And you build that, train those neural networks, right? The weights of WI is one or whatever, etc. Right? For this input, here is the output. Do it for another input, another output. Once you do this, it trains the model, and then this whole thing runs just super duper fast, right? I mean, something that took 10,000 hours can run in minutes. So this is one of the technologies, right? I'm just going through it very quickly to show you the art of the possible. Because if you just did finite element, finite volume methods, you will kill yourself. It will not be a digital twin. So you have to train the model, either do sort of brute force parallel processing, which HPC, shared memory, MPI, GPU, etc., or do smarter ways through AI, or actually both. So that brings me to digital twin, right? And so the purpose of this is, you have a physical equipment from Applied, or a factory from a robot from ABB or something, right? That's a physical asset. And the digital twin, it's a model of that thing on the digital world, right? That model is through simulation. So you take a physical asset, the Applied equipment, and you have a model of all the equipment. You are doing this vapor deposition, you're doing the transforming the stuff, you're moving this, you're hitting it with a nail, right? Metal formings, whatever, right? That is the model. But then oftentimes people say a digital twin is just a model. No. A digital twin is a digital twin when you have two-way information flow between the physical asset and the real asset, right? And the model, right? So essentially you pull data from the physical asset, like the Applied equipment, and you are saying, I'm also simultaneously trying to predict what is going to happen, and I may be off by a little bit. I get the real data, and I correct it, and that's how I keep my simulation model as close to the real thing. That is what a real digital twin is. So now the question is, people have applied to different areas, including manufacturing, right? So technology very, very important part is, in our world, there's this thing called reduced order models. If there's one thing, you can create a digital twin of this physics stuff, you need to have a ROM. What is a ROM? Normally when you solve these finite element methods, you are solving like AX equals B, right? With 1 million finite elements, the matrix is 1 million by 1 million. It's a ginormous matrix. It will take you like 1 billion hours to run. Turns out from numerical methods, right? Go back to your days of matrix algebra, eigenvalues, eigenvectors, right? There are these things called principal components. There are certain vectors that are more important than the others, right? So you don't have to represent with all 10 million by 10 million. You can reduce it to 1,000 by 1,000 automatically using numerical real algebra. That is the math, right? This is not AI. It is just with going back to the basics. This is what we do. So we have these static ROMs, dynamic ROMs, 3D ROM, 2D ROM, all kind. That is the core of the technology that we have at ANSYS for building digital twins. But then what we found is that sort of digital twins can be built with two methods. One is based on pure AI, where you put sensors. This is what I used to do when I was at ABB. Put a sensor, collect the data, and then basically like we humans, right, before we fall sick, we have an increase in temperature, we have a stomachache, right? Those are symptoms of the fact that I will fall sick. So people use AI to do this kind of stuff, right? If you combine the physics with the AI, you can do sort of absolutely amazing things, which is the hybrid analytics that I'm talking about. That's the core technology, right? The hybrid analytics. And then we have put in the accuracy of the prediction goes significantly higher with the hybrid. So that's the key technology. Based on this, right, we have a flow to do digital twins of stuff, right? So we can take an applied equipment and build a digital twin of that. So that's the key thing. And we combine it with the physics, the AI. Now you apply to manufacturing, right? So you have all the equipment, right, in a factory. Each of the equipment you build a digital twin and you make a digital twin of the whole factory, right? Powered by AWS, by Azure, et cetera, et cetera. Now you do it for the semiconductor factory, which is the problem I started with, right? So with TSMC and so on and so forth. Then I'm going to end my presentation saying that this is not something we can do on our own. We have partnered with Rockwell Automation to create a model of a factory, and with their tool called Emulate 3D, you can build a real factory model and then commission it and say, this is how it will work. Or working with NVIDIA. I started with NVIDIA, right? So we are working with NVIDIA. In fact, Jensen in his GTC keynote talked about ANSYS as the first partner. Why? Because he's building the Omniverse, which is all these things, right? On a screen, you can do fantastic graphics to do all this funky stuff, but he needs the physics model to model all those physical assets, right? That's where we come in. We are building those physical models for all the things on the Omniverse, powered by AI which is also powered by NVIDIA, and powered by HPC, powered by these things, right? And then finally, I want to end acknowledging that I have not taken Om's permission, but I've just decided to use his thing. We are actually working closely with applied digital twin. I think Alav is going to talk about that. So it's a fantastic opportunity, and I'm sorry I went a little fast, but I wanted to excite all of you in the audience that this, as President Biden wants to bring manufacturing back, as people are building greenfield factories, right? The opportunity of a smart factory is enormous. Thank you very much.